My name is Terrence Markin, and I'm the Executive Director of the Graphene Council, the largest community in the world for graphene producers, researchers, application developers, and end users. We have hosted the Graphene in Healthcare and Medical Applications Conference Series, and the video you are about to watch is from that series. We're going to hear from Professor Plentz from Brazil. He's going to talk about graphene field effect transistors.
So this is called Medical Shift Project. It is run at my university, UFMG, and funded by Brazilian Development Bank. And so, what's the idea here? No, you have your blood, with a lot, of floating molecules there that you want to detect, right? And maybe you want some specific molecule, like a virus marker. So what we do, we take the surface of the graphene and we bind to the surface of graphene some markers, also antibody or aptamers. We use either antibodies or aptamers. Our focus is more on aptamers. And so once you do that, if you have a non-specific molecule, it will go there, but it will not attach to this sensing molecule. But your specific molecules will go there and will attach to that antibody or to that aptamer that is on top of the graphene surface. Okay. So once you do that, but to do that, to measure that effect, you have to be able to measure some property of the graphene, right? Okay. And in our approach, we do that using a graphene field effect transistors. So this is an overview of what we have. We use graphene on top of silicon substrate. So you have your source, your drain, the usual field effect transistor configuration. So you put your sample here, a drop of blood or saliva or the sample you want to measure. The molecule of interest is within the sample. And what you do, you measure essentially, you measure the source to drain voltage or resistance or measure the current, and you apply a gate voltage to that sample to measure what is the response of the device. When you have the molecule you want to see, and when you don't have the molecule you want to see. And the nice thing, is that tiny modifications in the graphene surface, can have a very large effect on the way, that transistor will give you an electrical response from this gate voltage you apply in the sample. You can modify the charge in the device. This is the more usual way. You can modify the mobility of the device, but either way, you see that on the transistor response to that pulse in the gate voltage. So the key issue here, is that the graphene surface is very sensitive, but it's not very selective. So make the surface selective is really the key point here. So the graphene FETs are a very good platform to do that. And in this case, we have few players in the market, because there are hundreds of papers, but to make like thousands of the devices, all the devices working, all giving the same kind of response to a given molecule that you can detect, that you can decide if this is a positive or negative with reliability, is not a very easy thing to do. And there are many people, many companies trying to do that right now. And in principle, it is a universal platform. You just change that molecule that is attached to the graphene surface, and you have another sensor, right? So how to make that? So you have a molecule, you have a target molecule that is bounded to the antibody or to the aptamer, right? And what you have, once this happens, you have an electrical signal. So this is actually what we are measuring. This is an actual signal of many devices. So what we see, we apply a pulse of voltage in the gate, and we see, how the current or how the voltage, in the channel will act, or will respond to that gate voltage. And what you see here, for example, is an experiment where we have the human serum, that is albumin, with different amounts of the spike protein of the COVID. So this is the recent work. And you can really see that you can really make a decision whether there is COVID or there is not COVID. It's very clear in the sensor response to that gate voltage pulse. And the nice thing is that, and we do that because so this is some technical details, but in many of our recent work, we are using these pulsed measurements, because in that you can really enhance your ability to measure what's going on in the graphene surface. There is a paper here. There is a very interesting paper to read, and that puts this problem. It's not very easy to really measure in a real environment with high saline strength. Another way to do that, and we do that also, is to measure the current voltage characteristics under a gate voltage. So this is more like a DC experiment, right? And we do that in a very simple way, using an oscilloscope. Here you can see, we put a triangular wave in the gate, and just measure, the graphene characteristics. So this is the Dirac, the usual Dirac curve that you expect from the graphene. And you can really see that when you put only a saline solution, we have this kind of signal. When you put the human serum albumin, you have the green one, and you put the human serum albumin with COVID or SARS-CoV-2 S1 protein, you have the red. Okay, and one very important thing is that is that many papers, many experiments, and many things we see. We use only like a saline, a buffer solution with the protein of the interest, but there is no interferent proteins in there. So this kind of experiment does not tell you very much about the selectivity of the device, what is very important. In our case, we put directly the protein of interest in a few femtograms for milliliter in human albumin serum. That is your body plasma. So there are thousands or hundreds of interfering proteins there. And the important thing is that you can really show that the device is selective, right? You can really show that you can detect that virus protein there, that is in like floating around, many other proteins that won't interfere in your experiment. So this is very important, right? So one thing we do in our project is that we put the focus on what we have to do. We don't have all the infrastructure. So, for example, for device fabrication, we worked a lot at EPFL, using their facilities at Stanford and University, at Cornell University, using the Cornell Nanofabrication Facility, Stanford Nanofabrication Facility, Center for Micro Nano Devices at EPFL, but also very other institutions in Brazil. Fiocruz, for example, is a very important institution in Brazil for biotechnology. We have a partnership with that institution to do that kind of thing. So we have our main project here, but you can access infrastructure or knowledge everywhere. And so this is how the project was developed. So what we do, we have this is how we do the experiments. We have our devices there, in the probe station, but measuring the device in the probe station is not like it's very fine to develop the sensor, but it's not very fine for industrialization. So what we did in this project, our focus is industrialization, right? So from the very beginning, we didn't want to produce like only a few devices. No, we spend a lot of effort in really developing a high-scale production technology using graphene transferred to silicon. So, so this is a real image of a silicon wafer. By the way, this is a Grotex wafer that we got in the last fabrication we did. There was in the beginning of this year at EPFL. So we can so this wafer has, I guess, like more than 1,200 devices. Here are the devices. They are 2.5 by 2.5 millimeter. These ones. Here are the GFETs, the graphene field effect transistors. And we also developed a very cheap and reliable technology for mounting these chips on a very simple and very reliable card. So this is this chip can simply be mounted here by a flip chip technology that we developed. And here you see the devices. So you put your drop here on top and you make your measurement. So everything we did can be industrialized. So right now, we are if you do the cost breakdown for 100 millimeters wafer, we are at $1, but we see no really problem or big barriers to get to cents of dollars prices for those devices, because the technology we develop for fabrication and for backend is really very good and compatible with all the technology we have in the microelectronic industry. So this is one big photo of this device. So this is so the last time we processed 5 wafers from Grotex, in fact. And here is the device. So you can have, for example, mixed technologies. So here you have the substrate, but you have here, for example, an SU8. There is a polymer layer that is protecting all the devices, but the graphene FETs. So you can mix in the process you develop. We developed many technologies. And one important thing, this is that this chip here is already diced. That is a critical step, as you know. And here are the GFETs. You can see that you have very clean, very, very good graphene channel. And from here, we go to functionalization, and we have very good devices. So that wafer I showed you has 1,000 wafers, and we processed 5 wafers with like 100% yield. So we can really move this to an industry of very large scale, right? And so we also developed this reading platform. So that is like that. This is a real image. So we have here all the functionalities of reading the sensor and connecting to a cell phone software where you can do everything. So what we are doing now, we are moving all the instrumentation that we use in the probe station to like that, okay? And so one example here, this is the detection of Zika virus. This is a Zika virus biosensor. One important thing to say is that in our sensor, we do not measure only a few sensors. This is one of the reasons why we had in mind always from the very beginning, okay, we have to be able to measure hundreds of sensors, right? So to make it really significant, statistically significant. So this is one example where we have a sensor. This is a sensor for Zika. So you have the sensor. So you apply like only the saline solution, the buffer, or you apply the buffer with proteins that would give you a negative result, like CA or dengue and Zika. That is the one you want to detect. It is very important to say here that Zika and dengue, the proteins for Zika dengue are very close one to another, because they are parents virus. They're basically the same family of virus. But you can really detect that. And what we did, this is part of the project, since everything is connected, and all the data processing can in principle be done in the cloud, right? So we did some studies using multivariate analysis and artificial intelligence to select or to decide what's the positive, what's the negative result. So this is the output, for example, of a neural network that was trained to make this distinction between positive and negative. And the red dots here are the Zika sensors. So you can see that you can really separate the positive, that is the Zika, from the negative, that is not the other, what you want to detect, right? And you can also tune how much false positive or false negative you have. So this has many interesting features. This is an example for COVID. That is the most recent work. You can really see that when you put human serum, you have the black curve. When you put human serum with the S1 spike, you can see the red curve. This is one way to measure. You can really see there is a very big difference in the sensors. Another example here is this one, right? So the black curves here are only the sensor measuring the saline solution. There is no interfering protein. Here, this curve here is the saline is the human serum, only human serum. This red curve here is human serum with the protein of interest. That is in this case is the spike protein. So you can really see that you can differentiate very clearly the curves. And this is not only one measurement, right? This was measured in several sensors we fabricated and prepared. So the idea here, that device I showed you is connected to this software here. That is all in Portuguese right now, but I hope sometime it will be in English, French, Chinese, everything, right? So the idea is that you can use that to generate heat maps of diseases that are georeferenced, right? You can use this also like to use in your home. This is the actual device, and this is the actual card, right? So you can have your own health management or family health management. This can be a platform for services, right? This is a business model that is interesting, right? You can bundle with these other services, and you have, of course, the applications for the agribusiness. What is very interesting because it has a much lower fast time to market, because the regulations are not as strict as they are for human applications, right? But everything, you can make sensors for everything, basically, right? And what we did, using uptimers, I don't know if you are, I don't have time here to go in details, but uptimers, you can think of them, they are not like antibodies, but you can think of them as artificial antibodies, right? They are different molecules, completely different, but they do the job of an antibody. And the nice thing is that you can select it for anything, basically, right? And what we did within the project, we developed all the technology to produce and to put the aptamers on top of our sensors. So what we did for Zika, that sensor that I showed you. So we did for foot and mouth disease for agribusiness by 2 different ways. We did for SARS-CoV. This is the most recent aptamers we developed. We did for the subunit SU of the spike protein. We did also for the nucleocapsid protein. There is also interesting protein for the Zika virus. And just now we are finishing this protein here for the Brucella abortus bacteria. That is a very problematic bacteria in agribusiness also, right? So, what we try to do within this business, this project, this idea, is to have all the parts, all the pieces we needed to have a full production line, from selecting the proteins to making the devices, to functionalize the devices, to make the softwares and to make the electronics, right? So I already told you about that. So we have many biosensors in one platform, right? Basically for many in really low cost. So we had an investment about $2 million in 5 years. The researchers here, PhDs, masters, electrical engineers, chemistry technicians, students, everybody working together here. I am the PI, and João Luiz Neves is the CEO of the company that is working with us and is in the project financed by the Brazilian Development Bank. Right? Here are some papers that you can look at. There are we have published it. The most recent one is in the Sensors journal. It is about Staphylococcus aureus detection. Those others sensors and for Zika and for COVID, we are not publishing yet. But the results are there and very, very reliable. So I know that this is very fast, but it's just a very quick overview. So you can see what we are doing, what we have. And what I can say is that we really have a platform here that can go to industry, right? And Jeff told you about for example, the GrowTex capability. They can do like 200 millimeters wafers, with 200 millimeters wafers, you can have a lot of sensors in one wafer. And the production method is really compatible with the very standard industry, microelectronic industry. So we think that this can really be cheap to produce. So this is it. Thank you.
Thank you, Flávio. That's quite a tour de force to show how far you've come with this. And the one thing that really impresses, well, there's many things that impress me about your presentation, but one of them is your holistic view of the problem and working through not just the technology of the detection medium, but how to integrate it into the reader and just the like I said, the holistic approach to solving this problem. My question is, you guys have come this far with it, basically to produce a complete product. What are the next steps for you and for the company? What do you see happening next?
Well, right now, what we're looking for more investments. Basically, what we want to do is to completely finish that product, that remote platform, right? With all the integration, everything, to have this ready, and really move all the development, all the measurements, everything, to be done only with the cell phone and the remote platform. Because this is what is really necessary if you want, and use all the softwares, everything, because this is what is really necessary for you to do like hundreds or thousands of testing to really qualify your product, right? So the next step we are looking for partners for investment to do that. So we will move this everything really to the to TRL 6 or 7, right? And to move like very close to have a product that we can really qualify as that, right? This is the next step of the project. And we think now we have in mind that within with the proper investment, we can have this working in a hospital or a farm or whatever within like 1.5 years, 2 years maximum, right?
Excellent. Well, Flávio, we have a number of questions and only just a few minutes to ask them. But another observation, obviously, is the wide range of application here, not just human health, but also agricultural applications. And I also think that your concept from a public health, right, public health monitoring, where you'd have real-time sharing of data on geolocation for incidences of illness, is really quite fascinating, and I think really useful. My question is, how many different pathogens can you test with one chip, or is it really one chip per one pathogen? And I'd also like to hear how sensitive is this testing? I didn't know necessarily what the load factor was when you were doing the viral testing. You know, what kind of viral load? In other words, can you use this for a very early detection system, or, you know, does it need to have a fairly high load factor?
No, I mean, for the COVID, for instance, we have we know that we can easily detect like 100 femtograms per milliliter of the spike protein, right? We can do lower. Now we have devices that with 1 femtogram per milliliter, you can really detect it. So it's very sensitive, very sensitive, and the other question is that in that card that I showed you, right?
Yep.
This card is made for one device. The device there is 2.5 by 2.5 millimeters, right? I mean, I imagine that as we move on, we will reduce the size of the devices and everything will be much more efficient. So you can readily plug in this card other devices. So our mounting technology is really good for doing that.
Excellent.
So you can have a multiplexed test, right? And probably, but I don't know how to do it yet. Ideally, I would like to have in one chip, different transistors with different functionalizations. But this is more difficult to do. The way to go, I think, is to put many devices in one card. This is faster and this is reliable, I think.
Excellent. There is a very technical question that I'm going to have to pass to you separately, because I think that's going to be a multi-minute, and we're coming up to the end of the hour. But the one last question should be easy to address fairly quickly, because we just have a minute. How the results from the graphene FET compares with the conventional testing methods? Have you compared your test method with conventional testing methods?
No, we haven't. No, with Fiocruz, that is the Brazilian foundation that takes care it's a very big institution here in Brazil. This is one thing we want to do, right? But this is part of that other part of the project, where we really want to move to that validation step. Because we measure everything like in femtograms or nanograms per milliliter, but this is not the usual way. When you have like ELISA testing, for example. So we have to move on that. Benchmarking our test with ELISA, for example.
Excellent. Well, with that, Professor Plentz, Flávio, I want to thank you very much for sharing this information. I want to congratulate you on the tremendous amount of work your team has done in a short amount of time with the funding that you had, which, while not insignificant, is also not a tremendous amount considering everything you've achieved. We're also very happy to have you as part of the Graphene Council. And if anybody has any questions and would like to learn more about this technology, please reach out. On behalf of the Graphene Council, I want to thank everybody for participating and for your interest in this sector. Clearly, graphene has a very important future in healthcare applications, whether it be for devices, medical sensing, diagnostics, or even in some of the infrastructure of gowns and devices and elastomer products, etc., that can be enhanced with graphene. So with that, I want to thank you very much. Thank you for your interest in the Graphene Council. If you have any questions, if you need any guidance, if you need information, anything to do with graphene or any of the companies that you saw in the past 2 days, please reach out to us, and thank you for your time and attention.